fist fights with brass knuckles. I love to get right with the fifth and make your ass buckle.
So now I'm going to give you a list of some basic trigonometric integrals, okay? So integrals, so like sine and cosine and things like that. So first of all, the integral of sine x dx is going to be equal to a negative cosine x plus c. And then the next one, here I'm just going to list them, and you can go yourself and figure them out or verify them. It's pretty easy, you just differentiate each side once. So then this one's going to be a sine x plus c, and then the next one is going to be secant squared x dx. So this one you can kind of think like, okay, what when you differentiate it gives us this secant squared x, and that would be a tangent x plus c. Okay, we have a couple more. So then we have our secant x tangent x. So what when you differentiate, what can you differentiate to get this thing inside? And that would be a positive secant x plus c. And then I have a couple more, so I'll write them on the side over here. So integral of cosecant squared x dx is equal to a negative cotangent x plus c. And the last one is going to be the integral of cosecant x cotangent x dx. And that one is equal to a negative cosecant x plus c. Okay, so we have a total of 6 here. Here's 1, 2, 3, 4, 5. There's 5, and there's 6. Okay, so we have these basic trig integrals, and like I said, it's always good, not just with these ones, but with any kind of integral that you do, to make either a mental or a written check to make sure that the equation does work when you differentiate both sides. Okay, it's always good to verify that. Alright, now we have a special side note on our e to the x function, okay? So when we have the integral of e to the x dx, that's basically just going to be e to the x and then plus a c, okay? Because remember when we differentiate, the derivative of e to the x is just e to the x, unless we have something else in the exponent there, right? Or something in front. But anyways, that's basically going to be it. So that one's kind of special. Something else to note, so here's a new little topic. So basically, for all functions, for all kinds of functions that you see, so for all functions, when you, instead of an x, when you plug in what's called kx plus b, so that's like some linear form of something. So k and b are constants, okay? When you plug that in for any spot, for any, anything, or any spot, I'll say, then a factor of 1 over k must appear from the integration. So a factor of 1 over k comes out of the integration, and I'll just end it there, but I'll keep talking. So it comes out of the integration, and that's to counterbalance basically what happens in the chain rule when you go in the opposite direction. So let me show you an example of this. So let's say we have a function of called cosine kx plus b, and then dx, and we're integrating this, okay? So when you integrate it, instead of just having our positive sign of that same thing, so sine of whatever's inside, what we're going to have to add in the front is a 1 over k, this factor here. And then along with our plus c, of course, because when you differentiate both sides, so if we ddx both sides, let's do that. Okay, and then we have another, we're going to differentiate once with respect to x, so that'd be 1 over k, sine of kx plus b, and then plus c. So when we do this, the left side, we just get this cosine kx plus b, cosine kx plus b, and then that should equal 1 over k, and then when we differentiate that, we get a positive cosine of that same thing, plus, according to the chain rule, we have to bring out that coefficient on the x, so that'd be a k plus c. Well, not plus 0, plus 0. There we go. But anyway, so see how here, this k that we brought out, we needed this factor of 1 over k already in the front, so that those two can cancel out to become a 1. And we actually get the cosine kx plus b on the right side, as well as the cosine kx plus b on the left side. Okay? So remember that whenever you have some kind of linear thing inside with a coefficient on the x, then that 1 over k, we have to have 1 over the coefficient in the front somewhere attached to it. And that concept, in fact, is the same with e. When you have e raised to the kx plus b power, and you want to integrate it, then we have to have that same e to the kx plus b, and then add that 1 over k in front, along with your plus c. Okay, so then that way, when you do the chain rule and you do bring out a k in front there, then that cancels and becomes a 1 in front as a coefficient. Okay. So now for the last topic, and it's called initial conditions. Initial conditions. So far, we've been dealing with indefinite integrals, right? So, and indefinite integrals, they're pretty much variable and they're flexible because of that unknown constant that comes out in integration. Because our antiderivatives are not unique, remember, there are multiple solutions and they can differ by a constant. So, when we have an indefinite integral, that basically means that we have, because of that plus c at the end, so we get something, something, something plus c, and because of this plus c, that means we have infinitely many solutions, basically. Infinitely many. But now what we can do is we can actually, solutions, there we go. So now what we can do is we can actually pin down a particular solution by imposing or using what's called an initial condition. Okay, so what an initial condition allows us to do, so initial condition, such as, and I'll give you one, like y of 0 is equal to 4. So that means when you plug in x equals 0, you get out y equals 4. So when we have an initial condition like this, well, what it forces us to do is find a particular or a specific solution. Specific solution, okay? And I'll show you an example on the next slide. So let's say we have, we're supposed to solve the following. So dy dx is equal to 4x to the 7th with initial condition of y of 0 is equal to 4. So this thing here, what it means, solve that. See, we don't have an integration sign or anything, or an integration symbol. What this means, this is called a differential equation. Okay, so this is a differential, because we have the dy dx. Those are differentials, and it's an equation because of that equal sign, right? So to solve it, basically what we have to do is solve for y, okay? So in order to do so, we just rewrite the problem. So dy dx, and then we have 4x to the 7th, okay? And what we're going to do is basically just integrate with respect to x on both sides. So we integrate and we add that dx. So on the left side, what we see is these dx's cancel, and the d here cancels with the integration, so we just get out y, okay? So y is equal to, and let's integrate this guy here. So we have that 4, we can move in front, so integral of x to the 7th dx, okay? And then continuing, we get 4 times, according to the power rule, we're going to add a 1 to the exponent, so we get an 8, and then we have to divide by that new exponent. And we can't forget our plus c, because here we're dealing with an indefinite integral, meaning we don't have limits limits of or for integration. Okay, so then continuing, we have the 4 cancels with 8, so we get 1 over 2. Okay, so y is equal to 1 over 2 x to the 8th plus c. Alright, so normally we'd be done. This is our general solution, okay? That's what it's called, is our general solution. But now, on the next slide, I'll show you how to make use of this initial condition in order to find a specific solution. Okay, so we ended up with y equals 1/2 x to the 8th plus c, and we know y of 0 is equal to 4. So this is our initial condition, and what we're going to do is, this means that our x, when we plug in x equals 0, we get out an answer of y equals 4. Okay, so x equals 0, y equals 4, and we're going to plug those into this equation here, and we're going to solve for c. We're going to solve for our unknown constant. So if we plug in a 4 for y, then we get 1/2 times 0 to the 8th plus c. So this term is a 0, and we find that c is equal to a 4. Okay, so now that we have this piece of information, all we have to do is just plug it back into our general solution, and then by plugging in an actual value for c, we get a specific solution. Okay, so this is going to be y is equal to 1/2 x to the 8th plus 4. Okay, and that's basically it. This is our specific solution. We have solved the differential equation. Okay, all right. So that's it. That wraps it up for our concepts video on antiderivatives, aka the indefinite integral. So that's pretty much it, and I hope that helps, and good luck on your homework.
I love to punch straight niggas. Rooted waking, food is taking lunch meat niggas. Y'all motherfuckers phony, the father told me.